Cationic UV curing is a process in which resin molecules undergo polymerization and cross-linking when exposed to ultraviolet light. At the core of this process is the use of cationic photoinitiators, which generate reactive species under UV light, triggering a chain reaction that hardens the coating. Unlike traditional solvent-based curing, cationic UV curing does not rely on volatile organic solvents. It is speedy, energy-efficient, and environmentally friendly, producing virtually no VOC emissions. These characteristics make it particularly suitable for high-speed manufacturing environments that seek sustainable solutions. Cationic photo-induced polymerization was developed in the late 1970s by Dr. James V. Crivello, working at the General Electric Corporate Research and Development Center in New York. He was tasked with finding an alternative to the traditional thermally cured, solvent-based, electrically insulating enamel that had been used in the production of transformer generator cores. The primary goal of the project was to eliminate solvents. Free radical UV coatings were under development at this time, but when it was concluded that a curing unit with 20 mercury arc lamps and a nitrogen purging system would be required, it was deemed too expensive, and alternatives were needed. This led to the development of onium salt photoinitiators for cationic polymerization and the first successful application with photo-curable epoxy generator core plate enamel. As the oxonium ion and carbocation are inactive to oxygen, there was no need for any nitrogen purging step. Cationic UV cure mechanism. Photo-induced polymerizations proceed by a chain reaction mechanism involving the propagation of an active center by the interaction with a monomer. The active center can be a radical, a cation, or, more rarely, an anion. The photogenerated active species is the true initiator that can initiate the polymerization of a reactive monomer, usually by addition to a multiple bond, or by a ring-opening process. In general, a photopolymerizable formulation contains three key components. 1. A photoinitiator, which absorbs the light and generates the active species. 2. A reactive multifunctional monomer or oligomer, or a mixture of both, that gives rise to a cross-linking polymerization. The backbone of the oligomer can be varied widely and is designed to confer specific mechanical and physical properties to the polymerized material. 3. A reactive diluent, the role of which is to adjust the viscosity of the mixture to an acceptable level for application to a substrate. It also participates in the polymerization reaction. Photo-initiated cationic polymerization exhibits many of the same advantages as free radical photopolymerizations. One of the main advantages of cationic systems is the absence of air inhibition, a property that eliminates the need for an inert atmosphere during curing and clearly distinguishes cationic from radical polymerization. Cationic polymerization, once initiated, is non-terminating and can continue to proceed for a considerable time after the light source has been removed. This process is generally termed a dark reaction and results in further monomer conversion, either on standing or on thermal post-treatment of a sample. By contrast, free radicals are extinguished by a variety of bimolecular termination steps, and polymerization quickly ceases in the absence of light. Furthermore, cationically photopolymerizable monomers and reactive oligomers are generally characterized by inherently low levels of toxicity and irritation, and for this reason are good alternatives to acrylates and methacrylate systems usually employed in free radical photopolymerizations. In addition, the lower volume shrinkage observed in the cationic photopolymerization of epoxide monomers affords better adhesion properties as compared to the corresponding radical-based systems. Last but not least, photopolymerizable cationic systems possess better inherent mechanical properties and thermal resistance than their corresponding free radical system counterparts. Cationic UV-Cure photoinitiator. The chief photoinitiators used in cationic polymerizations are onium salts. The good thermal stability and excellent latency of onium salt photoinitiators in the presence of highly reactive multifunctional monomers at ambient temperature have made these salts very attractive for practical applications in photocurable formulations. Onium salt photoinitiators are ionic compounds that are composed of an organic cation paired with an inorganic anion. The organic cation is the light-absorbing component of the ion pair and the source of the photochemistry in these compounds. For this reason, the structure of the cation controls the UV absorption characteristics, photosensitivity, quantum yield, and whether the compound can be photosensitized. It also determines the ultimate thermal stability of the onium salt. On the other hand, the nature of the anion and its stability determine the strength of the acid formed during photolysis and its corresponding initiation efficiency. The nature of the anion also determines the character and reactivity of the propagating ion pair in the polymerization. This has a direct impact on the kinetics of polymerization and whether the eventual termination occurs. In the case of iodonium salts, UV irradiation induces both homolytic and heterolytic cleavages of Ri bonds to yield highly reactive cations, radical cations, and radicals. However, these are not the primary initiators of cationic polymerization. The initially formed cations and cation radicals react further with proton-donating species such as water or alcohols present in the reaction mixture to form Brunstad acids that are the primary initiating species. The initially formed species are much too unstable to remain sufficiently reactive over the delay period to initiate polymerization. Instead, initiation was attributed to the formation of a stable species, namely the Brunstad acid, derived from the anion of the starting onium salt. Cationically, photopolymerizable monomers. Photo-induced cationic polymerization has been used to carry out the carbocationic addition polymerization of unsaturated monomers such as vinyl ethers, styrene, and N-vinyl carbazole, as well as the ring-opening polymerizations of epoxy monomers, cyclic ethers, lactones, and cyclic acetals. Actually, the range of monomers polymerizable by a cationic mechanism is broad, and this permits the synthesis of a wide range of polymers that incorporate heteroatoms within the main chains. It was shown that monomers containing epoxycyclohexane rings display higher rates of polymerization than other types of epoxide functional groups, such as alkyl glycidyl ethers. Most often, cationic UV-curable formulations are based on one main ingredient, which is a cycloaliphatic epoxy resin commonly known as ECC. While some studies indicate a fast curing for ECC when cured under mercury UV bulb, the finished films often are very brittle due to a high TG. Conversion of ECC alone in standard conditions is usually in the range of 40 to 60%. Therefore, both brittleness and a low conversion degree often make ECC unsuitable to be used alone for industrial applications. In order to find the right balance between high curing speed, high conversion level, and limited brittleness, it is required to blend ECC with other ingredients. To achieve this, different components can be considered, such as 1. Other epoxy resins with a longer chain backbone, such as BS 3,4-epoxycyclohexyl adipate, which will show high curing speed and increased flexibility. 2. Other epoxy resins with a simpler structure, such as a monofunctional epoxy, such as cyclohexene oxide, which could cure very fast and reach a high conversion level. 3. Polyols, which will react through chain transfer and therefore influence the reaction speed, as well as bring flexibility to the cross-linked system. These polyols could have a polyester core. Dendrimers, or hyperbranched polyols, are of interest, and would be fully part of the formed polymer networks as reacting through the chain transfer mechanism in a similar way as the polyols. 4. Vinyl ethers and 5. Oxytanes, both well known as efficient reactive diluents, and therefore allowing to adjust the viscosity of the formulations while participating in the photopolymerization process. Some studies also report the benefits of blending epoxy with oxytanes, and that such systems do copolymerize well. 6. Another possibility is to blend cationic systems with free radical systems to form so-called interpenetrating networks, IPN, sometimes also referred to as hybrid formulations. Oxytanes benefits. Similar to epoxy, oxytanes react through a ring-opening mechanism. Oxytane rings possess a slightly lower ring strain energy than epoxy, oxyrane rings, while they show higher basicity of the heterocyclic oxygen, therefore making them have comparable reactivities. The photopolymerization mechanism of oxytanes, as well as their benefits, have been well investigated in various studies. For example, the monofunctional oxytane TMPO and the difunctional oxytane DITMPO are two efficient reactive diluents that can allow significant reduction of the viscosity of epoxy-based formulations while ensuring high reactivity in the cationic photopolymerization process. Lowering the viscosity of the formulations can increase the mobility of the reactive species during the photopolymerization process, and higher conversion degrees could be achieved when blending epoxy and oxytanes. Lower viscosity can be beneficial when applying coating or ink formulations on the desired substrates, which often results in a good visual appearance of the cured films. In 3D printing, viscosity is a key parameter. High viscosity is undesirable as objects would lack details. Cationic UV-curing applications. Cationic UV curing shows all the advantages related to UV curing technology, together with special characteristics due to the cationic nature of the reactive species. In most commercial applications, the formulations are based on multifunctional cycloaliphatic epoxides. This is because they show the highest photopolymerization rates, and in addition, photo-cured epoxy polymers possess excellent thermal mechanical properties, solvent resistance, and adhesion to a wide variety of substrates. Cationic UV curing process has found applications in the field of coatings, composites, adhesives, and inks. The cationic UV curing of epoxy monomers finds important applications in coatings. Photopolymerization of thick, greater than 1 mm, layers of monomers has found several applications in the field of composite materials. Using a cationic UV photopolymerization, it is possible to reduce the curing time to a minimum, achieving primer systems for high-speed processes. Functioning as a coupling agent, a UV-curable epoxy primer forms chemical bonds between the functional groups of the monomers and both the substrate and the subsequent coating. There is a growing interest in the inkjet process for industrial applications. From metal deposition to electronics fabrication and bioengineering, inkjet printing is emerging as the most versatile method for printing, imaging, and spatially controlling the deposition of liquids that has ever been invented. Critical for the use of UV-curable inks in inkjet printing are systems that have low viscosity, long pot life, working life, and are fast curing. The unique features of cationic UV curing technology, that is, the post-cure reaction that leads to a high degree of conversion, thus a low level of migration, the excellent adhesion to a variety of plastic or metal foils, and the superior mechanical properties make it particularly attractive for the formulation of UV-curable flexographic inks. In conclusion, cationic UV curing brings clear benefits such as low shrinkage and excellent adhesion to difficult substrates like plastic, metal, and glass. Cationic UV formulations are not sensitive to oxygen and benefit from the dark cure living polymerization, offering full cure possibilities. Despite these benefits, the use of cationic curing is very limited today, mainly due to the cost and limitation of available raw materials.